I'm delighted that we've got two more fantastic speakers today. And so we're going to start with Katherine Crichton, who's going to talk to us about what the geological past can tell us about the future, particularly of the Twilight Zone. So Katherine, over to you. Thank you.
I'm just going to share my screen. Okay. So hopefully everybody can see that. Right. Sorry, 1 second. Sorry. To reorganize some stuff here. Right, okay. So as Adrian said, I'm going to be talking about recent work that we've done, what the geological past can tell us about the future of the ocean's Twilight Zone. And just to note, this work was a proper joint effort between all the co-authors I've listed here. It's most likely the final paper to come out of a NERC project, which was funded and based in Cardiff University, and involved people from several academic establishments, and took long enough that a few of us even moved to a few other ones too at the same time. So those are listed down at the bottom. In this talk, I'll cover the major findings that we talked about in our recent paper, which was published in Nature Communications, where we use geological evidence to make a first estimate of the future of life in the ocean's Twilight Zone. You can see that paper on the screen. So as I mentioned before, this study came out of a larger question about the functioning of the ocean's biological carbon pump. We wanted to test the impact of metabolic temperature dependency on the ocean's carbon cycle. And we did this by combining evidence from the past ocean and system modeling. So I'll start just with a brief overview of the biological carbon pump and where metabolic processes and temperature fits into this. So here's just a sketch on screen. Photosynthesis takes carbon out of surface waters. And just to note, this process favors the carbon isotope carbon 12 over carbon 13, and this will be important for later. So the photosynthesis takes carbon out of surface waters, and this creates organic matter, including organic carbon. And this organic matter forms the base of the ocean food chain. A portion of the organic matter, including carbon, sinks out to surface waters. And as it gradually sinks, it's broken down by feeding, but also decomposition by bacteria. This decomposition or remineralization converts the organic carbon back into inorganic carbon and remixes with the water. Only a small fraction of the particulate carbon that leaves surface waters reaches the deep ocean, and less still reaches the ocean floor. So in our project, we focused on two major metabolic processes in the model, and these were photosynthesis rates in the surface, which in the model is the rate of nutrient uptake. And then the second process is the rate of remineralization of the sinking organic matter, or sinking organic carbon, particulate organic carbon, excuse me. According to empirical data, these metabolic rates roughly double with a 10-degree increase in temperature. And as the biological carbon pump is heavily dependent on these metabolic processes and gravity, implementing temperature dependence will make a big difference. So I've just highlighted these curves here, and you can think of these blue lines as the amount of particulate organic matter which is present in the water at that depth. So this would be a present situation, but in warmer water, these curves could look a bit like this. So in the warmer waters, the increased rate of remineralization on the sinking particulate organic carbon results in reduced organic carbon reaching the deep ocean and the ocean floor. So we use the paleo record to test whether this signal can be found in past warm climates. So the rationale for this whole project was we use data from the mid-Miocene to the present, which is 15 million years worth of global cooling. And in this period of time, there's well-preserved planktonic foraminifera, which are globally distributed, which were collected and collated for that project. So we could reconstruct past ocean conditions from these foraminifera. We also used an Earth system model, CGenie, which focused particularly on paleo-ocean studies in general. So using this model, we could simulate past ocean conditions, which include circulation differences, which are affected by changes in landmass and changes in bathymetry in the past climates. And so with the model, we could also then control the carbon cycle processes in the model ocean. So using these tools, we could try to answer the questions: do the reconstructed data conditions resemble those of a temperature-dependent biological pump or not? And what are the implications of this? So in near surface waters, temperature-dependent processes have an impact on the carbon-13 depth curve with warming. As I mentioned before, carbon-13 is important here, well, carbon isotopes. During photosynthesis, the carbon-12 is preferentially taken up over heavier carbon-13 isotopes from the water. So this leaves surface waters depleted in carbon-12 and makes them heavier. Using the delta notation, which is shown on this plot, this gives a higher delta 13C per mil value in nearest surface waters. As the organic matter sinks and remineralization occurs, the light carbon is released back into the water, gradually reducing the carbon-13 value of the water. And you can also kind of see that in this figure. Just to note that deeper than waters in the near surface, the impact of circulation and mixing of ocean water starts to dominate the carbon-13 signal rather than the metabolic processes. So that's why we're focusing on the near surface waters. By measuring the delta 13C in the planktonic foraminiferous shells, we can reconstruct the water delta 13C depth curve for our 7 time slices and 9 sites, as I noted here on the slide. So this is just an example site of what we did in that project, reconstructing these data points with the depth carbon 13. And then the thing that we're interested in here is the gradients of these data points in the near surface, because that can tell us about the rate of carbon cycling in the near surface waters. So we compared near surface waters around 200 or so meters depth, as indicated by the data. For example, this gradient is 82.1 meters per mil. And we compared that to two model configurations. One of them was temperature dependent metabolic processes, which are the red triangles, and another one, a standard model, which is not metabolic temperature dependent processes, which are the blue lines. And so what we're interested in is comparing the gradients of what the data says between our two and comparing our two model setups. So if we look at all the data and plot for all of the 7 time slices that we had in this project, it gives us the mean values. And this is what we come out with. And clearly the temperature dependent carbon pump is far better represents the data and strongly supports the hypothesis of the faster carbon and nutrient cycling in the surface warmer waters. So it supports this metabolic hypothesis. And this is just an overview of actually a previous paper, but it's really important as an introduction to the paper I'm actually going to talk about. So that's the paper we published in Science. At the same time, as part of that project, the depth habitat of many planktonic foraminiferous species, we reconstructed that as well, and also carried out abundance counts. So we're interested in what was happening to species distributions down the water column over the cooling period. And here's an example of 3 sites which cover low to mid latitudes areas over the last 15 million years with the time axis on the time on the x-axis. Foraminifera species both moved deeper and evolved to occupy deeper habitats over this period of global cooling. And we proposed that this was due to gradually increasing or improving food supply to depth. Because as you remember, I said, with the metabolic hypothesis, in warmer waters, less food in form of carbon and nutrients is reaching the deeper ocean. So conversely, in cooling, more food in terms of forms of nutrient carbon is reaching the deep ocean. Now moving on to our most recent paper, we summarized the findings that I was just talking about there from the middle Miocene, 15 million years ago to the present. and also added further evidence from the Eocene, which is around 50 million years ago, with waters that were warmer still than the Miocene. So just as an indicator, the Eocene mean temperatures are about 8 degrees warmer than present, and the middle Miocene around 5 degrees warmer than present in our model setups. And this isn't so different from the data indicators from these past climates. Of key interest here is that in the warmer climates, we find fewer, if not none at all, foraminiferous species in the Twilight and Mesopelagic zone. This is compared to a relative abundance in the present. But just to note that of these planktonic foraminifera, there are still many more species living in the near surface waters, just to note. So as I just mentioned, the past warmer climates show reduced Twilight zone life relative to today. Just to demonstrate here the effect of the temperature increase in our model on the metabolic temperature dependent biological carbon pump. Here I'm showing the low latitude and global mean down column curves for temperature, particular organic carbon flux, dissolved oxygen, and carbon-13 of dissolved inorganic carbon. So that this is the carbon-13 of the water seen essentially. Just note, less POC, particular organic carbon, is reaching Twilight zone depths in the warmer climates. Even though there may be more organic carbon, particular organic carbon, which is being exported from the surface. So you can see that in the second panel. Dissolved oxygen is very much reduced in the warmer climates, and the oxygen minimum zone is shallower, it's shoaled compared to the present. And the near surface delta 13C depth curves are quite different for the present compared to the warmer climates. And again, this is demonstrating the signature of increased carbon cycling and nutrient cycling nearer to surface water, nearer to the ocean surface. So to summarize so far, data from the Miocene and the Eocene support the metabolic hypothesis. A temperature-dependent biological carbon pump results in reduced food supply to depth in warmer climates. And paleo data suggests reduced number of species living at depth in past warmer climates. So expanding the questions then, we can ask, what does this mean for future anthropogenic warming in the Twilight zone? And what does the geological data from the past predict for the future? So to consider these questions, we forced that our CGNE Earth system model, which has a temperature-dependent biological carbon pump, as I mentioned, with 3 future emission scenarios, which can be thought of as a low, medium, and high scenario. So for example, the F625 means a total of 625 petagrams of carbon released to the atmosphere from 2010 onwards. This isn't a constant emission, it's a, I can't remember what it's called, but it peaks and then falls off. Sorry about that. So these forcings are applied as CO2 in the atmosphere, shown here on these curves. And the model's resultant surface ocean temperature is also plotted on these curves. And we ran those simulations for over 10,000 years. And it's just important to note that there's a change in scale on the X time axis here at 2500. So that's why there's some things dashed on there, because there's a change in scale. So the effect on particular organic carbon export and delivery to depth is shown here for both the global mean, which is a dashed line, and for the low latitude mean values in the model. And then to the right of these panels are the paleoclimates for comparison. So you can see the top panel B in the top graph in panel B is the POC exported from the surface. The second panel is the percentage of that POC, which is reaching 600 meters. Bottom panel is the percentage that was exported from the surface, which is reaching 1040 meters. So 600 meters is the middle of the Twilight zone approximately, and 1040 meters is what may be considered a sequestration depth, where the carbon is then sequestered for thousands of years. So we found that although POC export is increasing, which is a result of the increased nutrient uptake rates driven by warming, the POC reaching the inner and deep ocean is reduced compared to the present. This is a result of the increased rates of remineralization, the respiration process. We also found that compared to past climates, the POC export was lower in our future scenarios than for the comparable warming in the Miocene, which actually means that the food supply to depth was relatively worse in the future scenarios than it was for the Miocene scenario. So to turn this model output, particulate organic carbon, into something understandable for what may happen to life in the twilight zone, we use this model POC flux, or the percentage that arrives at 600 meters depth, and compared this against the abundance counts data at 600 meters, because as I mentioned, as part of this project, we also carried out abundance counts, which can tell us about how many of these foraminiferous species were living and at what depth. So using data from our 7 time slices, we then created a simple linear model, which is linking POC, or food supply, to abundance of foraminifera. And I've shown here an example of that process. So in the top panel is the percentage of total foramin community at 600 meters. These percentages are quite low, but as I mentioned, there's a far larger proportion of foraminifera actually living in the surface. So even though they're low, they're still significant numbers. That's the top panel. And the bottom panel is the model POC flux, again, over our 7 time slices since the middle Miocene, which is time is the x-axis. So if you plot those two things against each other, we can start to create a linear model. So for this site, kind of like this. So here is using all the sites that we had appropriate data for, and we could create our general linear model, which is here shown as a black line, and with this one standard deviation shown as the shaded portion of this graph. And we use a general model because we know that there's obviously uncertainties in our reconstructions and in the model, and we didn't want to have some bias for certain sites which may be more closer to, well, they're all open ocean sites, but they all have slightly different characteristics. So the rationale that food supply drives the potential for all life in the twilight zone, this is the rationale we apply, because these are planktonic foraminifera, but we want to talk about what might happen to all life in the twilight zone. And the basis of using this data to say that is because we think that food supply is going to be a control on anything that's living in the twilight zone, not just planktonic foraminifera. So just to note that all the sites that we used here, they're all only low latitude open ocean sites. So in our model, we're applying it to low latitude zone. So here's the model again on the left. And as I mentioned, there's a thick black line with one standard deviation shown as the shaded region. So we directly mapped this onto the POC flux in low latitudes at 600 meters as predicted in the model and shown here on the right panel. And we plot the change in the percentage of our foraminifera community, which, as I mentioned, is a stand-in for all life in the twilight zone. And we plot that as a percentage change and compare it to the situation at the start of simulation. So you can see that here on the bottom panel, which are some quite drastic numbers here. But this is all based on how much particulate organic carbon, which is essentially food, is actually arriving in those twilight zone depths. And for the high emission scenarios, you can see there's a really big drop in particulate organic carbon that's arriving in the twilight zone. And this is not compensated by increases in export from the surface. So this is really a first step to try and determine the vulnerability of life in the twilight zone in a future warmer world. Evidence from the past suggests a far emptier twilight zone, and based on this data, without strong emission mitigations, which lead to high or mid-range warming scenarios, life here could be seriously depleted. And also, as an aside, we didn't consider the direct effects of other drivers of change, including reduced oxygen, directly on life in the twilight zone. So other stresses such as pollution or overfishing or acidification are also not included, but will surely have an impact. That's also impacting twilight zone now. So just to wrap up, the geological evidence shows a more empty twilight zone in warmer climates of the Cenozoic for the last 66 million years. Temperature dependence of the biological carbon pump results in reduced food supply to depth on ocean warming, which has implications for the whole ocean carbon cycle as well. Anthropogenic warming could lead to massive disruption and diminution of life in the twilight zone as a direct result of this warming. Other stresses will also likely impact life in this zone. And just finally, we didn't consider extinction in our model. So our model, including the time it takes for recovery, may be a best case scenario. Thank you for your attention.
Thank you, Catherine. Fascinating stuff, absolutely. So let's see, so I haven't seen any questions. Steph, would you like to come in with a question?
Yes, hi Catherine.
Hello.
That was absolutely fascinating, really interesting stuff. And I admit I hadn't read the paper, and so I was really looking forward to this talk because you saved me a whole afternoon's reading by half an hour talk. So I was interested in your final results where you suggested that the amount of life, I guess is that biomass, I suppose, in the twilight zone could decrease as a result of warming. And I was wondering, in the model, so you're modelling the decrease in the amount of food arriving in the mesopelagic through export directly. Is there also something in your model which allows food to be generated mid-water through, recycling of organic matter and breaking down into smaller particles, which then can provide more food?
Well, to me, the whole ocean food web starts in the surface. That's where the carbon is essentially created, taken out of the water, and that's only by photosynthesis. So I think once you've left the surface waters, you're not going to be having new carbon being injected into the food web. So my answer would be no. I can't think how that would be possible. I don't think there's anything. I mean, there is in the model we account for obviously carbon cycling, so things that are coming out of the surface waters, it's being decomposed, and I mean, not in the model, but in reality it's being eaten.
Yeah.
But it's not necessarily something's being eaten at the surface. I mean, I suppose it's possible something can be eaten at the surface, and then what's left of that can be released in mid-ocean waters. I suppose that's possible, but I think in terms of this study, because we're looking at the geological past and the patterns that we see and the reconstructions that we do fit the idea that temperature dependence is really the thing that's controlling the carbon cycling in the water. I think that we can have quite a lot of confidence that even if there are other processes like that, they're not going to be overriding this really strong controller.
Yeah, I mean, I guess it comes down somewhat to the details of the model, that linear model that you've got there. In the contemporation, we struggle to balance how much food is entering the twilight zone with how much we know is required by the organisms that live there. Mm-hmm. We often find a deficit. It seems like there's too much. There's too much consumption going on in the mesopelagic and not enough food supply.
Yes.
And the complexity of the processes happening in the twilight zone really makes it really hard to balance that budget. And yes. So, it's just interesting to reflect on how your model is structured and whether the difficulties we have in the contemporary ocean with our observations can tell us something about how your model's responding to the changes.
Well, I mean, you're absolutely right. This is a simplified model, but I think because there's not that much data that exists on geological timescales for actual carbon cycling in the inner ocean, this is really a first step to try and say, what do we think this might mean for the future? And even just looking at the past warmer climates, even without this POC abundance model, it's already looking pretty bad. So
yeah, it was fascinating. Thanks, Catherine.
thank you.
I think we can squeeze in at least another quick talk. So Alexi, would you like to ask a question?
Yes, thank you. That was a great talk. So I haven't read the study admittedly, so this is my first introduction to it, but I'm going to read it. I'm curious, how is respiration included in the model?
In terms of in the food web, entirely.
Yeah,
Okay.
yeah. Are there consumers included, or is it just like one set respiration rate?
In this model, we don't have a food web in the surface. In the surface
Okay.
ocean, there is a representation of photosynthesizers that take nutrients out of the water depending on light availability and things like that. And then as part of this generalized surface ocean life, there is a portion, I believe, of carbon that is released back as respiration. But then in the end, it's just going to be like a plus or a minus.
Okay.
So that, I mean, there's no, in this model, there's no representation of that, those consumers in the surface, which then respiring.
Okay. Okay.
So what we have is actually an export production model.
Right.
So
Okay. Wonderful. Thank you.
So let's give us a try if we can be really quick. So Illy, would you like to ask your question?
Sure, I'll ask quickly. I was just wondering how applicable you think these results may be to higher trophic level organisms such as mesopelagic fish and other things inhabiting the water column.
yeah, well, I think it must be applicable. Obviously, those kind of creatures move around. They're not really stuck there. But then that's why I was also mentioning about, sorry, skip through, oxygen, for example. Food supply is something that's quite important, but also oxygen levels, that's going to be affecting these kind of animals. So I think a conclusion we can say from this study is, yes, we think food supply is going to reduce, but also oxygen in those conditions will change. So it's almost a kind of unknown situation. But because we think oxygen will reduce in twilight zone depths and food supply will reduce, you know, there's going to be implications for those kind of creatures. So there'll be either they'll have to move somewhere else or go extinct.
Great.
Quite strong language, but you know,
Yeah, that's
conditions will change.
Nice choice to face. Right, so I think we should move along then. So Catherine, thank you very much.